the schedule, the proposed schedule, and we'll start the week of October 19th on the presentations. Remember, you get 10 overheads, 10 minutes. We'll have a few minutes for discussion of whatever you present to us, and people can ask questions, and hopefully we'll get about 3 done in an hour. That hasn't really been a problem in the past. And we may try to go between 9 and 11 to get 6 done a day and be done within about a week or 6 days or so. Okay, Professor Slocum asked me to give you he called it hyper apology. He thought the class started at 10, okay? We're trying to reschedule, see if he might come in one of the last couple of days. Simone has listed the schedule for the rest of the semester. We should finish on October 15th with the lectures, the 24 lectures, 12 from him and 12 from me. I'll be lecturing Monday and Friday of next week, and then I'll be doing the 13th and 14th. And we should finish on the 14th. Okay? So, we were talking about engineering involves trade-offs and decisions. And I'm starting to talk about how do you make decisions, which really gets into how do you think. Okay? But I did talk to someone else this past week, Dave Rigoni. Anybody working on batteries? Nobody's working on batteries? Something called a Rigoni plot, the Dave Rigoni. Dave's about 85 now. He used to teach in the department. He was a graduate of this department, and he went on to do several things. He mentioned, when I was talking about some of this, his comment was a scientist solves problems that can be solved. An engineer solves problems that must be solved, okay? A scientist will, if there's a problem that they want to solve, they feel they have the capability of solving, they will simplify it until they can solve it, okay? An engineer, on the other hand, doesn't have the luxury of simplifying the problem. You know, you got to build the bridge all the way across the river. You can't build it halfway. Okay, if there's a problem with going all the way, you got to figure out how to complete the job. That's why a number of professors in engineering schools are merciless on the problem sets or the homework sets. If you don't get what they define as the right answer, you get 0 on there's no partial credit. Because to an engineer, doing the job even partially incorrect is a failure. Okay, you got to get it 100% right. Scientists, well, if we're in the right ballpark, but the scientists will write it down with differential equations and everything else, and so they feel very confident with their final solution. That runs into problems, okay, sometimes. And the example I was going to tell you is Brian Josephson. Anyone know who Brian Josephson is? You ever heard of the Josephson effect in superconductivity? Nope, nobody's ever heard of it. Okay, well, Brian Josephson was a graduate student in, I think, Cambridge rather than Oxford, but anyway, he's at a British university, and he was brand new graduate student, like 21 years old or so, 22, whatever, and he went in to see his professor. His professor was sort of busy and said, here, go solve this problem, and this was a problem on electron flow that people had written down the equations before and solved the problem many times. This was just sort of an exercise to keep him busy and for the professor to see how well he could do on a kind of a graduate school type physics problem. Well, Brian was naive. Brian didn't know. He wrote down the terms in differential equation for the forces on an electron as it's flowing through a material. And he wasn't smart enough to know that one of the terms is just usually thrown out and you set it to 0, right? You've done those solutions, right? You look at the differential equation, you say, oh, this term is insignificant. We'll drop it, right? Well, Brian was actually a good enough mathematician. He solved the problem with that term that everyone else simplified it so it would be easy to solve. He actually solved the harder problem, and he discovered the Josephson effect, which is basically electrons tunneling through materials. And that was like 1962. Before he was 30 years old, he had won the Nobel Prize. How about that? When I met him in the early 70s, he was sort of a basket case. He was in his early 30s, and everyone was just fawning all over, oh, this brilliant person, and just because he didn't know enough, okay? And he was actually a pretty humble guy, and he didn't have much personality. He didn't know how to take all these people fawning all over him and everything, okay? I mean, he's a nice person, but anyway, there's an example of, in general, the scientists all knew you throw out this term, and another person comes along and is too stupid to know that you don't do that, and he wins the Nobel Prize for being too stupid. There's also the quote from Frank Whipple, who was the British engineer who developed the first turbine engine, and there were predictions. He did this in the 1930s and early 40s, and there were predictions by other scientists when he was working on this. This is impossible. You know, remember Lord Kelvin's quote that something about powered flight, human-powered flight, or something is impossible, or something. Well, Kelvin was wrong, and it turns out people were telling Whipple that you couldn't build a turbine engine; it wouldn't work. And his quote was, "It's a good thing I was too stupid to know that it wouldn't work." Okay, because he made it work. Okay, he was an engineer. Okay, so one of the differences is the scientist will solve the problem or simplify the problem to where it can be solved. An engineer has got to figure a way around the problem. Then another thing that came out recently was MIT Spectrum came out last week, and here's the quote from Raphael Reif on his introduction. MIT solving problems together for the benefit of mankind. Okay? That for the benefit of mankind is sort of an engineering definition. Okay? The scientists are not solving problems for the benefit of mankind. They're solving problems to increase human knowledge, okay? Which they say, well, that will benefit you somehow in the future in some unspecified, vague way. MIT focuses on problem solving in service to the world. We stop worrying about boundaries between disciplines and focus instead on what it takes to solve the problem, making new tools, seeking new perspectives, and inventing new solutions. They solve the problem that must be solved, not the problem that can be solved. Interdisciplinary creativity, complex challenges. Remember, I define, or actually the School of Engineering defined engineering as complex, ambiguous, uncertain problems. And they also talked about bonds of mutual respect. So I thought this ties together some of what I've been talking to you about. And I didn't even prime him to say these things, okay? So, and then last time I put up understanding, what's going on with this automatic focus? Not doing well today, is it? Okay, understanding how we make decisions means understanding how we think. And I started to talk about Kahneman's book, this psychologist, I guess, PhD, okay? As someone pointed out, the difference between a psychiatrist and a psychologist, one's an MD and can prescribe drugs, okay? Anyway, so Kahneman won the Nobel Prize for trying to figure out how people think, and he came up with this System 1 and System 2, and we're going to talk a little bit about that. And I started talking about, well, I guess I can put up one of these other things. I'm missing one of my things. Anyway, I was talking about heuristics. There's System 1 and there's System 2. Oh, okay, here it is. This is what I was looking for. This is, remember I told you that people have written synopses of Kahneman's book. This is a 30-minute summary of Kahneman's book because it's a pretty dense book to read, okay? It'll take you a while. Save it for Thanksgiving vacation. You know, turkey will put you to sleep. His book can put you to sleep. Anyway. So chapter 1, he basically says there's two main processes in the brain. And they're not really different parts of the brain or anything, but as they've studied things, people, they can divide the system into a system 1 and a system 2. And system 1 is intuitive and automatic. When you see the stuff in bold in capital letters, you don't have to make a mental effort to read it says thinking fast and slow. If you see a stop sign, you know what that means. You don't have to worry about it, okay? And you develop all kinds of habits and things in your own life about when you brush your teeth and how you go, whether you eat breakfast before you get dressed or whatever things. People develop certain things that become what's normal for them, and that just simplifies a lot of decisions that you have every day in your life. System 2, on the other hand, requires skill, attention, and effort, and there's a fundamental assumption in Kahneman's book that basically the brain is lazy, okay? We like to find heuristics or other things, habits, to allow us not to have to make a decision about everything that happens in our life. We would just be, if we had to analyze everything that occurs, we wouldn't have time to do anything else. So out of pure survival, System 2 is not invoked except when System 1 can't deal with the problem, okay? And a lot of this is not, you don't see it as a problem, you just kind of, something happens, okay? If you saw a ball of fire just, form in the corner over there for no reason, we'd all have to start analyzing what happened. Where did it come from? We've never seen that before. It's not within our normal experience. Okay. Chapter 3 goes on, self-control and deliberate thought are both forms of mental work. That's System 2. Some people can experience a mental state of flow, and this is a state of joy and is considered an optimal experience. Has anyone ever had that? I mean, I was just talking to a guy, had breakfast with him, I had dinner with him beginning of the week. Today's Friday, right? And I asked him why he works so hard. Because he says, because of the rush when he solves the problem, okay? And I remember when I was doing a lot of research and had a dozen graduate students and stuff, a student would come in and we'd work on something, they'd show me the results, we'd talk about it. We're doing a System 2 thinking, okay? And all of a sudden the light goes off and you realize you just solved the problem. You now had a framework for the world and you could publish a paper on this, and there's a real joy. So I felt the flow, okay? He's felt the flow. The reason he works hard is he likes to get that rush. Maybe it's better than heroin. I don't know. I've never taken heroin, okay? But it's their thing. Anyway, he goes through associative activation where the process in the brain triggers ideas from other ideas. Priming effect, okay? The fact that if someone tells you it's going to rain and all of a sudden you see water coming down the stairs, you say, oh, the rain caused a flood, because you're already thinking about rain, okay? You're primed to think about and explain things in terms of something you just saw recently or in the past. You've been primed to think about things. A lot of the politics in the world that we disagree on is due to priming, okay? We see the American flag and we think patriotic, this is good, we share our wealth with the world. But in fact, and so when we were donating food to different parts of the world, we'd ship the rice or the wheat in bags that had the American flag all over it. Well, you'd get to Ethiopia or something, those people saw that as the worst evil in the world, because the American flag to them is primed as people who have come in and wiped out parts of their country, right? So we're primed to think of the American flag as something good, and other people are primed to think of it as something bad, okay? The whole ISIS thing, those people have been primed to think about certain things certain ways, and we think about things in different ways, and we just don't even understand how they make their decisions, okay? And we think, oh, they're destroying these ancient antiquities. Well, for them, on the ladder of abstraction or the Maslow's scale, it's more important to be religiously pure than to preserve some ancient art, okay? Whereas, well, we think ancient art is very valuable. and we'll trade it for millions of dollars, right? But to them, it's not important. So he goes through lots of the things, and the reason he won the Nobel Prize is because his work is so general, because it gets into how we think. This goes on, and I'll hand it out. This is nothing more than a summary of this 30-minute summary. This is the 5-minute summary of the 30-minute summary, okay? And it'll be on Stellar. I don't think it's on there yet, but it will be. Okay. There are heuristics we develop, and I talked about the one I used when I was looking at faculty resumes. If it took them too long to graduate from graduate school, they're not going to be very productive as a faculty member. I'll show you another heuristic that I used, because I haven't been giving you very many of the engineering stories. So a number of years ago, I was asked to evaluate why a pad eye failed. I'll show you what a pad eye is in a second. But what was happening, Johns Hopkins University, that does a lot of research, well, Johns Hopkins University has an applied physics laboratory, which is sort of like MIT's Lincoln Laboratory. The applied physics laboratory is mostly funded by the U.S. Navy, and a guy got hit in the head by a piece of metal while he's aboard ship out in the Pacific. It was a research ship being operated by Johns Hopkins, and it was towing on a cable some little object that we weren't allowed to know what it was, because the project was classified. We do know there was a submarine involved down there. And so, it's sonar test, folks. Okay, they're running a sonar experiment. Right there in Annapolis, Maryland at that time was the head sonar laboratory for the U.S. Navy, right across from the Naval Academy. I used to spend a couple of weeks there each summer, and I was in the welding building. Across this nice courtyard was the sonar building on the second floor, where all the hush-hush stuff and the computers and stuff were. You could walk through the first floor with just a bunch of pumps and other things. One time, and you could walk anywhere you wanted there, and I always thought security was sort of lax there, and I mentioned it, and they said, oh no, someone walked through the wrong door to get up to the second floor, and they said within 2 minutes there was a shore patrolman with a gun behind every tree pointing at that building. Okay, so they do some classified stuff for how to detect submarines and stuff. That's why I drew the object as sort of a submarine cigar-shaped object. So anyway, they're towing this object, and there's some submarine involved, but we just didn't know exactly what they were doing. But up on board ship, there was a pad eye. A pad eye is nothing more than something that has a hole in it, and this piece of steel, which was about 1 inch thick and maybe 5 inches long by 5 inches or whatever, maybe 6 by 6, had a 1 inch hole in it, had a weld that welded it to the bulkhead of the ship, and they had a cable, a steel cable going through here, and the pad eye the weld had broken, and it shot across and hit this guy in the head. He wasn't killed, but he had some brain injuries, and at the time he was also in prison for other things. That he filed this suit against the government, I think, I don't remember, or Johns Hopkins. In any case, if you looked at this thing, that round circular hole was now elongated. And it was sort of elongated down in the direction towards where the cable might be pulling through. And so, system one thinking, which failed first, the weld or the pad eye hole? The pad eye hole deformed, the weld broke. What came first, the chicken or the egg? The hole. Why? Yeah, Isaac Newton said something. For every action, there's an equal opposite reaction. What's allowing you to bend that hole before you broke the weld, or after you broke the weld? The pad eye is just a loose trinket on a chain at that point, right? There's nothing that's going to allow you. It's 1 inch thick steel. Okay, and you're elongating a 1 inch hole in a 1 inch thick piece of steel. It has to be the hole that elongated first. Did you know of the 5 or 6 experts that looked at this, they all determined the weld failed first? I'm not kidding. I was the only guy that said, what? Of course the hole failed first. one of my heuristics is if a piece of metal deforms before the weld breaks, the weld was a good weld. Because the weld doesn't have to hold any more strength than letting the metal deform. Okay? That's one of my heuristics that I've developed for System 1 thinking. Okay? But I'm a welding engineer. What can I say? Well, then there's System 2 here to try to differentiate these. In System 2, I had to do some analysis to prove it to these other people. Well, in the analysis, you actually have to start thinking a little harder. And here's our pad eye up on the ship, okay? And they had 10-foot swells in the sea that day in the Pacific. We know this was, I don't know we know the exact depth, but it was on the order of 2,000 foot length. Maybe I did know it at the time. This was years ago. And so to analyze this, when the ship goes up to the top of the swell, the cable has to stretch because this is way down in the bottom. There's a time delay here. The mass of this thing that they're towing is not going to follow the swells on the surface when it's 2,000 feet below. It's just going to stretch the cable. I wanted to know what's the load in the cable because I had to have enough force to deform that hole. That was my hypothesis, and I was going to try to convince these other engineers that the hole came first and not the weld failure. So 10 out of 2,000, 10 feet over 2,000 is 1/200th. You can do that in your head, but then, and that's equal to the strain. And so you could do this as force displacement, but it's easier for me to think stress versus strain. The stress is proportional to the strain if this is all elastic. This elastic stretching, putting a big load on this cable, is just Young's modulus, 30 million for steel times 0.005 is the strain, 150,000 psi. If that was a 1-inch square cable, you'd be talking about 150,000 pounds of force, right? 150,000 pounds might bend that little circle, right? In fact, I did the calculation. You can go further and you can do that calculation too. And in fact, it would, okay? So the analysis, this was work, you know. Actually, the example that I think I gave it to you last time that Kahneman likes to use is you can do this math problem in your head by System 1. The example he gives is 13 times 37. Most people will just ignore that and not try to multiply that out. They will do 2 times 2 automatically because they know the answer. They've done it before. Most of you don't remember the answer to 13 times 37. It takes mental effort, and you usually won't do it unless you're forced to, right? So those are some of the types of things that Kahneman goes through, and we've now discussed Kahneman. Now, in some of this, I guess I need to, what I was talking to the students about was the fact that I had not, I've been sort of using this class as a guinea pig. I didn't decide to teach this, what is engineering, until August. And I was going to teach about casting, a casting module that I taught before 4 or 5 years ago. I thought about, I had something else I'd been thinking about during the summer. But finally, about halfway through August, I decided, I'm going to do one as engineering. And so the reason this is somewhat disjoint is I've never taught it before. I didn't have a whole lot of time to prepare to start teaching it. I've sort of been assembling little pieces that I've been doing over the years, which is why I gave you the leadership thing. I did that 20 years ago. I wrote the article in 2003 on leadership management and education at MIT, and we talked about those things. Well, you got kind of that from, you know, you got a piece there and a piece there and stuff. And I guess it was partly Kahneman, my reading Kahneman this summer, they got me thinking, well, there's some interesting things in Kahneman, and it would be worthwhile for the students to read it. But a year and a half ago, I started writing a book called 50 Years at MIT. I've been here for 47 years, and I got a few more years to finish it. Actually, I have 7 more years to finish it, because I would like to have it done for my 50th reunion class, which is 54 years since I came here, right? So first I wanted to have it done in 50, on my 50 years here, but since I haven't been writing on it too much, but I actually have in some ways. And actually teaching this course is sort of supplemental to that, but I won't get into that. But last year, I've written about 70 pages on this book, and I'm about halfway through my junior year, so I got a few more years to go. But I decided to start writing down some of the heuristics that I've developed about how to survive at MIT. And so here it is. The only thing I've ever put a copyright on other than my thesis, okay, which MIT required me to do. But here's surviving at MIT. Some students have asked me to come and give a talk before. I actually used this as the theme of a 20-minute talk and handed out that same thing. Actually, you're getting the two-page version. Before I handed out last year a one-page version with just the first 10. Now I think you got 22 things on there. The first one is, and some of these actually, they do have to do with surviving at MIT. Be humble, but don't be humiliated. One of the biggest problems for MIT students is you think everybody else around you is so brilliant, and you feel like you're not up to snuff, when in fact you're in the top 0.03% of the population, okay? So you should learn to be humble and recognize that no matter how good you are at something, there's probably someone here who's better, okay? So you got to be humble, but don't be humiliated because of that. Just because someone's better, measure yourself against yourself, not by what others think about you, okay? Have the self-confidence to know that you're actually a worthwhile individual. Work hard, but recognize your limitations. You can read some of these things. Don't procrastinate. I've told you that several times, I think. 95% of the pressure at MIT is self-inflicted. Have self-confidence. Recognize that MIT is an artificial environment, and you're actually above average. You're well above average, okay? Here, you're just average, okay? Accept failure, move on. MIT actually is an elite institution. Don't apologize for it, okay? But use them to benefit others if you're an engineer, okay? Serve others, which is sort of the same thing. Somewhere in here, know the end from the beginning. And I said, find your career anchor. And some of you have already gotten, how many of you have already gotten career anchors? Anybody? You have, Teresa, right? You have a copy. Anyway, if you already have a copy, they cost $13, so don't take one if you already have one. But career anchors, I mentioned this guy, Ed Schein, who is a professor at the Sloan School, and this is a 30-minute quiz on which you will not be graded. Okay, so you can take one if you like. You have to answer 40 questions in the beginning on such things as, I want to be so good at what I do that others will seek my expert advice. Never, seldom, often, or always. 1, 2, 3, or 4. Okay? Or I am most fulfilled in my work when I have been able to integrate the efforts of others towards a common task. 1, 2, 3, or 4. Just be honest with yourself. I didn't say this, but if you want, you could Xerox those 3 pages or 4 pages on the quiz, and someone else could use this book afterwards, okay, if you don't write in it. But in any case, there's a professor over at the Sloan School. Actually, his name is on this edition. This is what, 4th edition? Yeah. John von Manen goes around giving this a half-day or a full-day seminar on this to people at companies on what's your career, finding your career anchor. Probably makes $40,000 or $50,000 a day giving these little seminars. Okay, that's why these books cost so much. But in any case, what is your career anchor? If you answer these questions, Ed Schein, who spent decades thinking about these types of things, came up with 8 career anchors. A career anchor is the one thing you will not give up when faced with a choice in your career or your life. And it could be something like lifestyle. I often say some people want to be a park ranger, right? It could be technical competence. You want to be a scientist or an engineer solving problems. It could be managerial competence. You want to help organize other people to solve problems. It can be, for me, my career anchor, believe it or not, my career anchor is autonomy. I don't like having a boss. And I have tenure, so I don't really have a boss. Okay, I do have a boss, but I can ignore him. It's called tenure. Okay, so I'm in the perfect job. I don't want to retire. I enjoy what I'm doing. My career anchor is autonomy. Okay, so there are 8 career anchors. Security. A lot of people who work for the government, they want the security of knowing they will have a pension because the government can just keep printing that money. Okay, all the rest of us, our savings will go worth nothing, but Congress will keep their pensions at some buying power, and they will make lots of money. Okay, or they will have security. So anyway, you can find your career anchor. If you're married, have your spouse do it separately, and then figure out what the two of you have, and you might find out whether, well, it's important to know what motivates you and those close to you. Okay, so you can read about lessons learned, which is the end of my book that I haven't finished. I wrote the end from the beginning. Okay. Here's another one-page synopsis. The other synopsis of Kahneman's book was the 30-minute synopsis or 30-minute summary. There's another one, How Do We Think? By the Curious Reader. It's sort of a Cliff's Notes version again. But did we have enough career anchors to go around? Do we?
We're one short.
Okay. Well, I have one. Okay. So pass it back. And this is a one-page summary, automatic system 1 and attentive system 2, where you have to analyze things. System 1's quick, impulsive, intuitive. System 2 is deliberate, cautious, effortful, but is also lazy. There's something called priming. I think we've talked about that. There's anchoring, the availability heuristics. He's got all kinds of confirmation bias. It's an I found Kahneman interesting enough to make it part of this course. And then I went over, there's a number of things that will be on Stellar about that if you want. There's another thing that I've been using for 15 years. And I have this because I was teaching a freshman seminar on things you needed to know. And I had come across this book, Fallacies and Pitfalls of Language, The Language Trap, by this Canadian, I don't know, he's a logician or something, S. Morris Ingle. And I have put on Stellar, or will be on Stellar, my synopsis of that. So I wrote my own Cliff's Notes for the students. And the date on this is December 2000, okay, that I wrote this up. And basically, I'm just paraphrasing the book, but Aristotle basically came up with what, 300 and some logical arguments, most of which, all but a couple of dozen of which he found were incorrect logically. And you can start drawing Venn diagrams of the logic things and stuff, but each chapter in the book, I'm not handing out the book, you can get one yourself, or you can, if you actually Google errors of logic, you'll find this document, okay? I was surprised. Somehow, I don't know how it got on there, but anyway. Equivocation, everything that you've heard some of these things. Everything that runs has feet, the river runs, therefore the river has feet, okay? Or the miracles of science, just by itself, is equivocation. Science doesn't deal with miracles. Science deals with facts. If a tree falls in the forest and no one is present to hear it, does it make a sound? Okay, that's sort of a philosophical thing, or I like the Prairie Home Companion version. Anyone know the Prairie Home Companion version? If a man speaks in the wood and no one hears him, is he still wrong? Okay, it's Prairie Home Companion makes all kinds of jokes about husbands and wives. Okay. Sweeping and hasty generalization. Complex questions. You've always heard the one about when did you stop beating your wife? When did you buy your first Cadillac? There's some assumption in that question, like you bought a Cadillac once, okay? Or you're beating your wife, okay? So the question it's a question you shouldn't try to answer because it's too complex to answer. Anyway, so there's a number of logical fallacies, and I now, particularly when I'm doing my consulting, and I'm on the defense, and some expert writes a report, I often will use this reference as a scientific reference on what's wrong with his argument. Okay? So it's not just, he's an idiot, of course the hole failed first and not the weld. You know, you can't write that. You say, he's got a hasty or sweeping generalization, chapter 8 of Engel, okay? And I give a scientific reference to his logical fallacy. Okay. Actually, that's the course I've been debating for 9 months. Students have been asking me to give a course on my forensic consulting. And I have been advised by several people, don't do it. If I start telling you all the secrets, if you watch all 120 hours, you'll get most of the secrets, but you're going to have to compile them yourself. But if I were to condense them in just a little 12-unit course and put them on the web, I was in a deposition yesterday. Every attorney that ever deposes me is going to have read those, or watched all of those, and they're going to know all of my little tricks. Okay? For example, I'll give you one of them right now. An attorney will ask you a question under oath, and he'll say, you give an answer explaining it, and he'll say, no, that was a yes-no question. I just want a yes or a no. And I say, the first I give a polite answer of, I can't just give a yes-no answer to that question. Yes, I want a yes-no. That was a yes-no question. Sir, I'm under oath, and I was sworn to tell the truth and the whole truth. To give anything other than my explanation would not be the whole truth. Okay? And some of these guys are really aggressive, and if they want to keep it up, okay, I want a yes or no answer. I'll say, sir, are you soliciting me to lie under oath? Because for an attorney, that's a felony. Okay? I've only done that 2 or 3 times in my career. But when I start saying, are you soliciting me to lie under oath? Boy, the room goes quiet. Okay? And no. Okay. So there are little tricks you learn over time. Okay? And you try to be polite, but the person tries to get aggressive. You still try to be polite, but after a couple of strikes, they're out. Okay? Lay them out flat. Okay? Anyway. A guy tried to stiff me on my bill once, and it's a long story, but I actually used the solicit me to lie under oath, and all of a sudden they came to the settlement table. Okay. Just changed it from a civil complaint to a criminal complaint. Okay. The scientific method. What is the scientific method? In fact, actually, I ought to put up one of my overheads. From the beginning, when we make decisions, we use a number of tools. Oops, that's not the one I want. Where did I put it? We don't have to have it. But think about the scientific method for a second. I'll find what I want. Okay. We talked about Kahneman. I talked about Morris Engel. Okay. This is understanding how we make decisions means understanding how we think. Kahneman talks about how we think from kind of a psychologist's point of view, or psychologist's point of view. Engel talks about it from logic, just pure logic, which is you can write down mathematical formulas, Venn diagram type things. And we also know that the scientific method is a proven method of discovery. So some of this stuff is sort of part of that kind of, what do I do in my forensics, okay? I'm using the scientific method to go back and analyze a problem. Okay, and I'm trying to make decisions on how this thing occurred. Okay, can I give you an example of something I've done this week? I have to stop and think. Nothing's coming immediately to mind. But I sort of get a rush trying to figure out, oh, I remember. I'll give you one that occurred last night or 2 nights ago. So there's a fire in a church in New York, and it was in the kitchen in the basement. And you have this little mom and pop shop in Ohio that's selling these, $15,000 commercial ranges, okay, ovens for cooking bread and heating up things on the stove and stuff. And since this is a materials course, the guys who design these ovens and sell them for $15,000, the commercial ovens, it's basically just stainless steel sheet metal. And these guys are sheet metal workers. They're not trained engineers. And so on the oven, this will be the back. This is the front with the door. And underneath here, there's a thermomagnetic valve that runs the pilot light. This is sort of an old style thing. It's 12 years old. And this is stainless steel. There was no insulation in this. I don't know why, but they didn't have any insulation on the walls. So it's just a sheet of steel on the bottom. And they ran an aluminum tube full of the gas for the oven up to this valve, screwed it in, and when the firemen came in, they saw the fire underneath the oven. They would extinguish it, and the flames would go out when they hit it with all their CO2 or their water or whatever. And then as soon as all the steam from the water went away, the fire would come right back. And they hit it again with their hoses, and a couple of seconds, 10 seconds later or whatever, the fire comes back. And they keep doing this 3 or 4 times. They know there was a gas leak down here. The only thing in the area of the gas leak was this, source of gas was this pilot light little tube made out of aluminum. So what's the problem? This is an oven that operates at, you might be cooking pizza or something. You can operate at 500 degrees Fahrenheit. You got a piece of stainless steel, and you got aluminum tube right beneath it with no insulation in between. Yeah. Yep, this is in service for 12 years, but it turns out when you connected this tube to the valve, they used a little brass or steel nut. I don't know which one it was, but it wasn't an aluminum nut, okay? And they had a little brass ferrule, a little ring in there that you crimped with a nut to tighten down like a tourniquet on the tube to make a seal. Well, every time you heat that thing up, the aluminum expands more than the brass or the steel because it has a higher coefficient of thermal expansion. When it cools back down, it's now shrunk, and I'm loosening the nut and loosening the crimp on the ferrule every time I cycle this. So, okay, do an estimate. 12 years in the church. How many hours has that been in service? How many hours a year do you think there might be on running a stove in a church? It's on the other thousands. I said, well, let's assume 500 hours a year, okay? Let's say you use it a couple of times a week for 5 hours. That's 500 hours. How many thermal cycles? And I estimated 100 or something, okay, twice a week. I mean, these are just estimates, but I take 500 times 12, and I get 6,000 hours of service. Okay, I go look up the creep behavior of aluminum. This is system 2, okay? System 1 was just kind of realizing, oh, I don't usually put aluminum tubes inside a hot oven, okay? Not a good idea. That's sort of system 1 level. System 2 is to go do the analysis. And you can it doesn't matter whether it's a heat-treated aluminum alloy or it's just a non-heat-treated aluminum alloy. The heat-treated alloys over a couple of thousand hours will lose their temper at 300 or 400 degrees Fahrenheit. So they're no longer heat-treated. They don't have the strength they should have, okay? So I don't know the type of alloy because the whole thing melted in the fire. I have to write a report about something that doesn't exist? Well, I can write a report about something that doesn't exist. because it was just a lousy job of material selection. If they had used a steel tube, which is what they use now, okay, it wouldn't have happened, right? So you don't have to prove everything in a court of law. You just have to, well, in a criminal case you do, but I've never done a criminal case. I don't usually do those. But you do have to prove things, what's most probable, okay? We know there was a gas leak there. The firemen saw it. The flames keep coming back, right? They put it out, it comes right back in seconds. It was a big flame, okay? So it had to be a big fuel source. It had to be gas source because solids don't burn that quickly, reignite that quickly. Anyway, you can go through and you can analyze it and you can say what's most probable on something like that. Okay, so I'd asked you about the scientific method. Okay, what is the scientific method? What's it start with? Anybody remember? No one remembers? Huh?
Observation.
Observation, yes. Collecting the data. And what do you do with it after you collect it? Create a hypothesis. Very good. Okay. Since you're now getting there partway, I'll save everyone the trouble. And this is the best. What happened to mine? Did I unplug it? VGA. Yeah, okay. Okay, thanks. So this is out of the National Fire Protection Association down here in Quincy, Massachusetts, not-for-profit 2014 edition of Guide for Fire and Explosion Investigations. About every 3 years they publish a new one of these. It's been around for about 20 years. It's a consensus document. Anyone in the country could write to the committee and say, I think you should rewrite this paragraph in your booklet. The booklet's about half an inch thick now, and every fire investigator uses this booklet. So chapter 4 is basic methodology, which is the scientific method. And in fact, the first figure, 4.3, in that chapter is the scientific method. Okay, recognize the need. Well, you know, okay, there's a problem. I think you don't usually worry about that first one. Define the problem, and then collect the data around that problem. And these four in here is really the scientific method, okay? You collect the data, whatever the thing is. I mean, okay, let's go back to this one I mentioned to you when Nancy Hopkins, a professor of biology, complained to Bob Bergeneau, who's dean of science here 20 years ago, that some of the women faculty were not treated equally with the male faculty. And Bob Bergeneau was receptive, but he wanted to collect the data. And so he found out what the salaries of the women were in the School of Science, professors, what was their office space in square feet, what was their student space per graduate student, what was their office space. He had the data, and whoo, she was right. So what did he do about it? He corrected it. The next year, they all got big raises to bring them up equal, okay, to the males in the department. Then Chuck Vest was the president, and he says, and actually MIT got a lot of good press in the Boston Globe, and Bob Bergeneau, who went on to be president of the University of Toronto, where he came from, and then he became chancellor of the University of California system. He's retired now. But he had a lot of integrity. He collected the data. The hypothesis of Nancy Hopkins was that women weren't treated equally, and the data showed it was true. Then Bob Bergeneau fixed the problem, okay, when he drew his conclusion. And did I ever tell you the story about, so Chuck Vest ordered all the other deans to do the same thing. You have to ask, why did he have to order them? Couldn't they, just by example, realize that was a worthwhile thing to do? But no, the president had to order the other deans because they already knew what the data said. They didn't want to know it, okay? And I sat in engineering council. This is towards the end of my term as department head. And I remember, because they were under orders of the president, to do an evaluation and see if things were not fair in other schools at MIT. They formed a committee, and Professor Gibson was head of the School of Engineering committee that was supposed to look at women's salaries and fairness and lab space and all that stuff. And what did she do? She asked Nancy Hopkins, I mean, sort of logical, well, how did you go about it, Nancy? So Nancy told her, well, we went and we collected the hard data. And so she made the exact same request to Bob Brown. Remember my great manager that I adore, okay, now president of Boston University? And Bob Brown announces to all the department heads that Lorna Gibson's committee has requested, salary, data, lab space, and all this other stuff. And Bob wanted us to discuss whether we should give it to him. Well, is that really a question? Okay? But no, we went around the table, and there are 10 department heads in the 8 departments because electrical engineering has 3 department heads. Okay? And just so happened I was the last one. We also had an associate dean who had a say. There was only one woman in the room, that was Donna Savicki, who's the assistant dean, and she didn't generally get to speak unless it was to clarify some administrative thing. Every person in that room, before it got to me, gave some reason why we should not release the data. This is the truth, okay? It got to me and I said, I don't understand, I don't believe what I just heard. The data is whatever the data is. If you resist this, the president's going to order you to give it to him, right? So why resist? Why don't you just go collect it, and then when you have the data, you can figure out what to do with it. And in fact, that's what they did decide to do, okay? Because it was just sort of logic, I mean, this is not rocket science on my part. This was just simple logic, okay? But I remember that whole example as how the dynamics of a meeting can have people thinking in ways that make absolutely no sense, okay? But that's a true story, folks. When my book comes out, it will probably be in the book. Okay, thanks. See you tomorrow. Oh, actually, I'll see you Monday. I'm lecturing on Monday.